For today's peanut combustion lab, you're going to need a triple beam balance to measure the mass of an unburnt and burnt peanut, some tin foil to protect the table from any rogue burning peanuts that may escape, some goggles to protect you from any flying peanut debris, your peanuts to combust, a peanut holder to keep them from escaping, and some matches to ignite them.
Okay, so today's lab is all about trying to figure out how much mass is lost due to combustion inside of a normal lightly salted peanut. So we know that the peanut is mainly your protein, fat, and your sugars or carbohydrates. There's some cellulose in there. But the point is there's a whole lot of combustible material. So we're going to try and figure out, as with combustion, anytime you add oxygen, a fuel source like this peanut, and a spark or a little bit of energy, you can get out CO2, water, and a lot more energy than what you put in. So we're going to see how much of this peanut is turned into CO2 and water. To do that, we need to first measure our peanut. And to do that, we need our triple beam balance. If we got to take the mass of our peanut, so we'll toss her on there. And then I use the 0.1 gram increment here until I balance it out. And our peanut looks to be about 1.1 grams. So we got a 1.1 gram peanut here. And now we're going to get the combustion reaction started. What we need now are a few matches. We'll angle this underneath it so we can get it started slowly but surely. Uh-oh. Try it again. All right. And we'll see if we can get this peanut going. Now, things to mention about this is your fat molecules are about 56 carbons long, and your sugar molecule is about 12, between 6 and 12, depending on how you want to look at it. Glucose is 6 carbons long, but then the actual full sugar molecule, that like table sugar, is 12. So you're looking at needing quite a bit of startup energy to begin breaking down these carbon chains into carbon dioxide. But once you get enough startup energy, combustion should start just like that. And we will go on ahead and let this thing combust out all of its energy. Now that the peanut is essentially burned its fuel off, we'll go on ahead and dump that peanut into our balance and get the mass. So looking at our results, it looks like our peanut now only weighs 0.3 grams. Meaning it's lost more than 0.7 grams of mass from this combustion reaction. And to top it off, there's still some brown left in my peanut, which means it hasn't fully combusted yet. So if I wanted to, I could probably burn off another 0.1 or 0.2 grams of this peanut from what's remaining. So let's see if I can actually do that. And looky there, we had some more fuel that we needed to burn off. So we'll go on ahead and get a good burn on this and make sure we got rid of it all. All right, so as you can see, we're now down to 0.2 grams on this, and that means that we've lost almost 0.8 or 0.9 grams of mass, so almost 90%, around 80 to 90% of the total mass of this peanut has been burned away, and you can see what remains is this charred ash. And this stuff right here, just to show you, you can crunch up and break up into powder, essentially. So what is this stuff that's left behind? Well, that's a good question. Not everything inside the peanut is actually combustible. So not everything in here is cellulose, not everything in here is fat and sugar and fiber and your starches and everything else. There's more to it than just that. In fact, looking at the back of your label here, you can see that you have calcium and you have things like iron and phosphorus and manganese. Those are not going to be combustible. So the stuff that you have left behind at this point in time is basically this stuff here. The rest of it, the fat, the saturated fats, the carbohydrates, and the proteins, all of those things are hydrocarbons, and they've all burnt off into the air. And that is the 90% of the mass that you no longer have. So with that is the lab in just about a nutshell.